Okay.
Super. So welcome to the second day of the IEEE 3DIC conference. Good morning or good afternoon in Europe and Asia. Where you are. My name is Peter Ramm. I'm from Fraunhofer EMFT in Munich, and I'm happy to chair the morning session, the session number 3. And we will be starting with the plenary presentation on 3D for more by Dr. Mustafa Badaroglu. You are here, Mustafa? Super. I think you are you in person here?
No, joining remotely.
Okay,
so that's all the way from Europe.
Okay, I thought you come in person. Okay, I'm also remotely, of course. So, just to introduce you, Mustafa Badaroglu is principal engineer at Qualcomm and responsible for the technology and architecture definition and development for products employing compute-in-memory technology. Before rejoining Qualcomm, he previously worked at Huawei, Qualcomm for a first time, IMEC, ON Semiconductor, and Tubidax Space. During his career, he had various assignments for the execution and management of mobile and automotive chipset designs, from concept to volume production, process technology pathfinding, electronic design automation, and design technology co-optimization. Dr. Badaroglu received his PhD in electrical engineering and holds a Master of Industrial Management, both from the Catholic University of Leuven. He holds more than 60 published patents and authored over 100 publications in scientific journals and proceedings. He is the global chair of IIDS More team, focusing on high-volume manufacturing roadmap of logic devices and memory. He is a senior member of IEEE. Let's welcome Mustafa.
So, thank you so much, Peter. Thank you so much for your kind introduction. So, I'm Mustafa Badaroglu from Qualcomm. So I'm happy to give the opening talk of this session and bring you some perspective of how advanced technology scaling goes in handshaking mode with the 3D integration. So that's the global message that I just want to paint the picture with. And the outline of my talk today is I will start with which drivers use for more scaling, as well as the scaling targets. And then giving a landscape of the devices we see in the next 15 years. And also particularly these devices have to talk to the memory. So the memory has a problem. And basically helping us some potential solutions and addressing them in my talk. The particular 3D logic memory integration has to do a deep dive look on multiple aspects. So those aspects I just want to cover is tier-to-tier I/O definition, TESS, thermal, and the cost implications, and finally some takeaways of what we extract. So from the application point of view, so we have the left, so the right-hand side here is how fast we generate the data and how this data is representative to the consumer. Basically, improved human-computer interfaces for advanced GPU, augmented reality, and also interactive sensing. And the left-hand side here is how the data generated, processed data generated from it with abundant computing being processed in the data center or in the cloud or even in the fog system, which can be a building or home-like environment. So that side requires a lot of memory and storage requirements, as well as the interfaces where you have an enormous amount of communication bandwidth necessary between the left and the right-hand side here. So the essence of it today, connectivity, how we see it, intelligence everywhere. So intelligence during communication, intelligence on the node itself. So on the data center, on the network core, network edge, and on the fog interfaces on the edge, base stations, and also on the devices themselves. So AI basically is distributed in all parts of this communication interfaces and also in the compute unit itself. So if we take this up, so you can clearly see this trend of artificial intelligence in terms of the edge and as well as the data AI, cloud AI. So there's a significant growth rate of these applications with an annual growth rate of around 25%. So this is a very, very impressive growth. And actually, most of the silicon volume is also dictated by this application because you need to put a lot of computation, enormous amount of parallelism is offered by this. So that's why consequently the silicon volume is also driven by this application. That's why there is a cost issue, especially for the edge AI, especially because of the increased silicon volume needed for this application, is also a significant concern on how to address it in a cost-effective way. But nevertheless, from a scaling perspective, this is what we have to bring as value to the consumer. So if you look at the market drivers of the more technology, so you have one set is the mobile application. So you see a convergence of a lot of heterogeneous integration of a lot of cores, like neural processing unit, as I mentioned in the previous slide, CPU, GPU, and domain-specific accelerators for application like sensing or biometrics. So that's basically enormous and heterogeneous computing happening here to be able to reduce the power and also improve the performance concurrently. And then the VR AR application, we call it extreme reality for enriched media, and more and more very advanced natural language processing, real time, and multiple edge AI applications from mobile phones to smart cameras and other type of sensor fusion application. On the data cloud center, typically the chipsets that we see is in 5 categories. So AI accelerators that are basically embedded together with a many core CPU core next to side by side to each other. Codec ASIC, processing GPU, it's all continuous. So, and it needs to have stringent reliability requirements. Networking chips, these are always on, extremely IO and compute intensive. And the power envelope is very, very high. You can go up to 500 watt power envelope. And then in the automotive ADAS chips and the memory IO solutions in general, for AI graphics and HPC, which are also falling in this category. So there are also a lot of platform chips which are basically spread across mobile, edge AI, and HPC application. And you see these type of computational platform like in the MPU fabric, also the fine pitch 3D stacking, reconfigurable compute fabrics, which is important for domain-specific reconfigurable ASIC, and also a full heterogeneous system with enabled by smart 2.5D interposer. So for the technology targets, we have one aspect is the technology itself, which is basically the device data path scaling. So the core technology scaling requirement. And the second requirement is the system scaling requirement. So on the PPA side, there is a clear slowdown, but today the observation on the power, performance, area, cost, temperature, and the schedule. So you typically see in a node-to-node basis about 15% improvement of performance at ISO power. And power reduction can be more than 25%. Area scaling at SoC level is scaling at with about 35% down. Wafer costs limited below 30%, and then translating into about 10% die cost increase. But we're for sure die cost reduction, 10% die cost reduction for the same function. But when you add new functions to it, you want to typically keep the same cost parity as much as you can. So meaning that actually putting 20% or more functions at every generation at the same cost. So on the temperature, so this is a big issue. So the power density is a problem, and we want to limit it less than 10% in a node cadence. There are also interesting requirements for the products. So every smartphone generation has to be delivered within every premium tier has to be delivered in a 1-year product cycle, while for the data center, it is typically a 3-year product cycle because there are a lot of additives coming with the system, which is which is fitting into the 3-year product cycle. On the system scaling, so these are on the device side, but on the system scaling, the most important thing is the TOPS per millimeter square and TOPS per watt concurrent scaling. And then translating into a single parameter here, performance at the area efficient performance and energy efficient performance improvement, which we call it TOPS times TOPS per watt divided by area. And typically in a node-to-node basis, we want to see about 2.4 scaling of this parameter. And this can be put for many, many things like per frame, per inference, per training, per packet, rather than a data path of a logic, but this is at the system level what matters for a given application. So you see clearly reaching the goal of performance improvement, especially with the new technology nodes, is getting extremely difficult. And so the one way to improve the performance is to invest on system level interconnect. And one of the main reason here for classical scaling, the density scaling is not going to be anymore, particularly for the SRAM to overall at the SoC level, it's very hard to reach the 35% scaling down of the area. VDD scaling, power supply voltage scaling has significantly slowed down. The parasitics improvement, even these days, it's not surprising to see 0.9 scaling node to node, but the target-wise 0.85 is already not at a good point already. So the increasing frequency is very, very challenging. So most of the chips are to be operated in the TDP limit, so thermally defined profile. And that's not that easy to basically increase the frequency right away in the chip to improve the performance. Other problem, and that's actually what we choose to do this for many, many years, increasing the number of cores or increasing the number of compute units. They are always coming with an overhead, like how to utilize them, how to basically map the parallel load, and how to provide a good busing solution to feed the data into those cores. So that's why there is the solution for system scaling, actually, because of these scaling challenges, introducing high bandwidth and high capacity memory has been basically the effort of the last 4 years, and then being actually defining maybe another 5 years ahead, which is improving the memory traffic augmented by the interconnect. And then that's why you see a clear trend actually to put more interconnect and memory capacity, and basically at the end achieving the bandwidth and capacity. The reticle size, interposer reticle size, is now reaching the 4 times of the reticle, which was reported by TSMC. And then also more heterogeneous stacking of the more disintegration is happening to tackle with the yield and also to tackle with the power density because of the targets that I mentioned above. And then the observation is basically you have about 2 times scaling of the tops per watt per area scaling at each year. On the other hand, the area of the interposer is increasing despite the fact that the chip size is decreasing. So that's an interesting observation of how overall system scaling still achievable at an amazing speed, 2 times speed instead of the 15% improvement of the performance. So if we look at the other side, the technology capability, from a device structure point of view, we were happily enjoying the FinFET for more than a decade, and it is expected to scale pretty well to 3 nanometer node around which is actually defined about 2022 second half. And then this is a very effective device because it's also exploiting the 3D direction very, very well. Taller fin, increasing the drive, and also reasonably better low power characteristics due to channel control. And then there is, you have heard about the announcements of the lateral gate-all-around device picking up. So that's, we call this nanosheet. And that's providing a much better performance than FinFET because of better footprint per drive. So this is allowing us to get more performance at a unit area from this cell. And also better low power and DTCO enhancement because you can choose the width of the device depending on the design rule, reduce the size of your standard cell area by carefully selecting the width of the devices in your SoC. Then 2030, it will be true sequential or extreme fine pitch 3D stacking. So device tiers put on top of each other. Basically, it can be logic on logic, logic on memory, or conventionally, for instance, P over N devices like CFET that will be defining the definition of these technologies, but they will be always based on the baseline device on gate-all-around device. And then more stacking generation with true 3D heterogeneous integration, for instance, different wafer substrates. Those kind of things might appear in the second generation of 3D, which is defining a full true 3D system in the cube. So if you look at in detail, so some pitch targets that we see in these devices. So the typical node cadence, we see a 2-year cadence until the 2022. So here this is an interim point starting with the roadmap, but initially every 2-year cadence you have one technology from 5 nanometer defined by 2020 has shifted to 3 nanometer nodes by projected to be in 2022. 2 nanometer node is projected to be at 2025, and then you have 3-year cadence. And the first parameter here is the gate pitch, and then the second is the tightest metal pitch that you see in the chip. So the end of roadmap, the metal pitch is saturating around 16 nanometer pitch. And the leading device having a crossover point, especially lateral gate-all-around device, picking up in 2022. And then the 3D version of lateral gate-all-around 3D device is picking up in 2031. And then this will be basically 1 nanometer equivalent nodes of defining 2021. So if you in terms of the channel material, so there's a transition to more because of the heterogeneous stacking capability. to silicon germanium to germanium channels, maybe 2D material can be a better alternative if the manufacturing solution is created for this. But this technology roadmap needs to go with fine pitch stacking technologies, where the stacking generation inflection. So initially, memory and logic applications with particle die to wafer stacking, and then true fine pitch stacking starting early generation in 2028, like P over N with layer transfer, and then the memory and logic and monolithic or sequential 3D by 2031. And in this generation, we already see early developments of all infrastructure material that was communicated by the leading IDMs and foundries. For instance, high efficiency interposer cap, high reliability I/O interfaces, power via TSV. This will enable already some 3D generations between the large gap of the nodes. For instance, a 3D version of the same CPU chip coming in the second generation, able to catch the 1-year product cadence, filling the gaps of the nodes. So this is a more high-level picture of this perspective. So you see on the upper side, 2D scaling for energy efficient computing at scaled area enabled by DTCO. So there is a early generation of nanosheet, and then because of the crossover point with the fine pitch scaling, it's going to be happening around 2028, especially for fine pitch 3D integration. So STCO enhanced nanosheet, basically 3D compatible nanosheet. And then going to the more logic application beyond 2030. So in the 3D, which is not actually alternative solution, it's really a complementing solution because memory is strongly decoupled from the first row here for the logic scaling, and the memory needs to be connected. And 3D basically generates for instance, first generation SRAM and logic, and then 3D SRAM or 3D DRAM and logic, and then the domain-specific chiplets, let's say active interposer, memory on the interposer, decap, NOC, and all the other infrastructures like I/O, ESD, and voltage regulation, which is at the end bringing the system scaling. So this is all requires a new levels of interconnect at various levels to connect to a fine pitch device to enable the system scaling. If you look at the perspective of how the device scaling, how do we get the area scaling? So until 2028, DTCO can still help for particularly for the logic device improvement. DTCO is reasonably okay. But on the SRAM side, there is a relatively a flattening curve, and then only pickup is possible for both logic device and the SRAM by 3D stacking, logic and logic scaling. So this point refers to 2-tier stacking, and this point refers to 4-tier stacking, where the equivalent CPU computational density and then the memory density will be improved by the roadmap generation. So that's for the density scaling of computation and memory. So on the DTCO side, this is a simple cartoon explaining how the area scaling happens with the DTCO. Although the pitch have not been scaling very, very aggressively, but still the device size was reducing. Basically logic routed size, block size was reducing quite impressively. First generations, it was done by the fin depopulation. So the fin so here instead of 3 fins, we use 2 fins, and then now we are in the generation of single fin devices, And then particularly with the nanosheet, because the drive for single fin is not sufficient enough, then you make more stacked devices with nanosheet and then place them more nanosheets on top of each other. And also some focus on some key design rules like contact over active, cell border definition, single diffusion break. This will allow to reduce the cell height and the width concurrently. And finally, by 2028, a CFET-like device with PMOS over N, which is basically further reducing the cell height to another leapfrog jump on the cell height by this generation, which is typically, this generation is around 1.5 nanometer nodes. So and one thing that is one of the biggest issue for the pitch scaling is in fact the interconnect resistance and power distribution problem. So usually the tight pitch interconnect has been accommodated pretty well, especially these interconnects are not really used for routing, but they've been mostly used for the standard cell port landing. So basically you can call this like a cell fan-out interconnect. In order to spread the connections of the pins to routing layers of the interconnect, you use the tight pitch interconnect as the port fan-out of the standard cell. And you see the aggressive pitch scaling already happening on this interconnect, and then a significant increase of the resistance. Unfortunately, part of this tight pitch interconnect has to be used also for the power distribution network. And that's basically where the most of the problem occurs in the definition of it. That's why there is a tendency to go to buried rail because of the significant increase of the resistance, not anymore satisfying the power delivery to the standard cell. But even with a solution that is like a buried power rail or other type of local interconnect solution, you still need to improve the vertical resistance. So that's why the technology has invested a lot on via resistance improvement by alignment control, by material change, barrier liner technology, and has kept the vertical via resistance relatively stable and projected to be remaining the same across the multi-node generation. Actually, this needs to be enabled because even you have a 3D power delivery solution, you need to go through that kind of via layer to be able to deliver the current to the cell, and that's or distribute to the other layers, other tiers. If the power comes from one side of the chip, but delivered to the second tier in the IC, which is placed above on the die, which is placed above a bottom die. So you need to reduce this resistance. So that's why there is a lot of material reliability and DTCO innovation ongoing to be able to improve the vertical resistance. And you have seen a lot of announcements that I will show in the next slides, particularly invested in this direction. So another reason actually why we cannot improve the clock frequency is this wire resistance. So on-chip wire resistance, as well as the device scaling at the contacted poly pitch, as well as the device pitch scaling, reduces the stress boosters, which is actually further improvement of the frequency is not that easy to get from the transistor. So that's why you see a flattening of the single thread frequency across the logic, even getting worse by 2028. But it will, at the system level, this will even be further dramatic because of the increased power density requirement to keep the thermal envelope. You need to throttle down the clock frequency, and that will actually, in the end of the roadmap, you need to operate the chips somewhere around 800 megahertz to be able, if you want to meet the same power density requirement. So although the power density scaling is reducing, but because of the additional 3D generations, which is coming by 2031, with respect to the starting point, we have a 4.3 times increase of the power density that is forecasted in the next 15 years. So now how do we get the performance, and how do we get how do we solve this power density problem? Basically, a 3D system with a jointly optimized 2D device is an answer to this. And you see here two examples of announcements. So first announcements has come from that I listed here is from AMD. So that's basically AMD 3D V-cache technology that was used. I think there are very interesting talks in the 3D IC conference about it. I look forward to hearing them. And so you can see that because of the cache capacity increase to tripling the cache capacity is improved to last level cache bandwidth to more than 2 terabyte per second. And then doing nothing in the 2D device, but only improving the memory controller probably. So there is an improvement of the gaming performance, CPU, GPU performance of more than 12% frame per second and 15% gaming improvement. So this actually enabled by 3D SOIC technology using hybrid bonding, which is basically creating a very fine pitch connection between the logic and the memory die. And then the second category is how to deliver the infrastructural components to 2D. So besides the 2D device, if you don't make the 2D device compatible with the 3D technology, so at the system level, you do not have gains, as I tried to convince you in the previous slides. So first thing is a DTCO improvement to enable the area scaling, so FinFET to nanosheet transition. So you can see here as an announcement of the 20 angstrom node, or equivalent to 2 nanometer nodes, transition to rebound FET, and then also delivering, making a power distribution problem, which is actually the delivering the power from the bottom of the via. So which is enabling the power distribution from the backside of the transistor. So that's basically coupling this PDM problem that I mentioned before, the high interconnect resistance problem, and also improving the density of the chip, because you have now less routing in the front side of the chip when you deliver the power from the backside. So these kind of innovations are now introduced as a more innovation at the device scale, which is actually making the 2D device 3D compliant, is an enabler for scaling. So which is actually emphasizing the message that I just want to trail. So this is primarily another problem is the power. So one of the reasons why power is not scaling, because of there is no steep subthreshold device. So VDD is expected to stall around 600 millivolts. And then with the nanosheet improvements and T-inversion scaling, you can keep the subthreshold slope around 70 millivolts per decade across the generation. And then for the other thing, for the C effective, like especially parasitic capacitance, there are a lot of requirements that can be things done in the gate-all-around device and material change, like in the low-case spacer, and then a lot of SDCO solutions covering the power scaling issue, because power scaling really virtually stops at this point. So like integrated voltage regulators or 3D power distribution network will be the savior especially for this S2C row that I mentioned here. So that's for sure development of parallelism, and parallel architectures are extreme requirements to take advantage of this. So This is I mentioned this already. So that was the observation that was mentioned. So memory wall problem. The one of the issue today between the memory and the compute core, basically it's hard to feed the data. So the one time you can have a bandwidth, so very wide bandwidth, but the capacity of the data is very, very limited. This is a typical cache problem. So for L0, you need 4 kilobit cache, and then for L1, maybe 256 kilobyte, and then for L2, 8 megabyte, L3, 64, 256 megabyte. But here, the data reuse, for instance, for an AI operation, is very, very difficult. You need to fetch the data multiple times and load this cache memory because you don't have enough capacity. So that's why it is not allowing to use the data between the kernels. Kernel is a process called, it's an AI channel. So it's for every filter, you need to load the data, but there is not enough capacity provided by this memory. So then you had to use really the off package and unpackaged memory subsystem. So you see that there is a very big jump here. So you go to a HBM3 system. So the difference between this cache is very, very big. And then or off-chip communication like DDR6. So the biggest issue for off-chip is particularly the energy consumption. So for DDR5, energy consumption is about 2 picojoule per bit, while for the compute unit, it's 5 femtojoule per bit. So not any more performance, but there's a big gap also in the energy. So for 3D, what is the actually attack point is how to tackle the big gap between the unchipped memory and unpackaged memory, especially to cover these 2 orders of magnitude difference in the memory. So to be able to do that, we need a bandwidth about 5 terabytes per second bandwidth and a higher capacity, more than 256 megabyte to enable this type of AI application. So because of this, a lot of things have been invested on the interposer size to bridge that gap, like concurrently improve the bandwidth and capacity. And you have seen, as I said, on the number of the HBM cores and also the interposer size, now 12 HBM DRAM cubes and the 4 times the reticle size, and significant increase of the IO bandwidth and IO single speed. So if you look at these numbers, basically the scaling is an order of magnitude faster than more scaling. So the gap in performance is tackled by improving the IO speed and the bandwidth. So if you look at a typical AI application, here I list down an example. So for instance, your Mac can operate at 1 gigahertz. So suppose that you want to process 16 pixels in parallel over 8 channels and over 64 filters. You need at every cycle, you need to feed an 8 kilobyte data to operate it at this frequency. So basically required memory bandwidth that you need for this type of application is 128 terabit per second. And this is mostly a read operation. So if you target any NVM memory, non-volatile memory, which is a very good read latency, but write latency is not that critical for this application, it can be a solution. The reason for this, actually, if you look at the on-chip cache trends, so the highest numbers that you see at the macro, at the integrated macro level, it's kind of 356 megabits. So it's a relatively small size compared to this target. So to fit this parameter, every parameter is a byte minimum, which is a weight, like an 8-bit weight. So this is the size of the memory that you might need in the application. So the 3D stacking memory, that's why it's enabling a very, very promising alternative to HBM. because with the HBM2 today, maybe we can enable 1 kilobit, and the communication with is about 700 femtojoule per bit. With HBM3, this number can go down to 350 femtojoule per bit. But the opportunity, if we enable a 3D SRAM with this, basically you can go to as low as 20 femtojoule per bit and enable already a 4 kilobit connection between the memory and the underlying CPU core. Basically, to how to generate this target memory with this application. So the integration challenges, a lot of integration challenges. So how to position the TSV and the IOs in that memory for area efficient allocation, as well as how to handle tests, how to deliver PDN to the power rail, and how to tackle the temperature requirement if the CPU die is directly below the SRAM. So rather than using a high bandwidth bus right away, so the synergy for improving the bandwidth is typically handled by network on chip connection between the SRAM die and the logic die below. I want to emphasize here one thing I just want to say. So for this IO solution, we don't have a better solution than the 2D. 2D still provides the lowest energy. And one of the reasons is explained in this slide. So you have, let's say, a 2D last level cache application here. So you need to still do the routing of a 2 millimeter, and you need to go to a bus where it is connecting all the macros to deliver the basically deliver the data. So you have a relatively long bus actually to get 64-bit or 128-bit data from the last level cache. So this loading of this 2 millimeter wire is about 500 femtofarads. So in the 2D solution, it's not possible to eliminate this bus unless you put the logic below if your thermal envelope is okay. And then if you go for a hybrid bonding solution, so with a light IO, you might reduce the tier IO loading penalty to 3 femtofarads. And then for the microbump tier-to-tier stacking, you might be able to reduce it to, you have an additional of 40 femtofarads. So on top of this 500 femtofarad, you have a 2 femtofarad from hybrid bonding and another 40 femtofarad from the, if you choose microbump routing, microbump stacking solution. So at the end, compared to 2D solution, there is always a 2D routing overhead and also additional tier-to-tier IO capacitances. So it's not a low energy solution. However, the low energy comes at the system level. Because of most of the DRAM accesses, so about 70% of the DRAM accesses are done for a compute application, while the rest is happening for the SRAM and the compute. So if we increase the capacity of the memory and improve the bandwidth, basically there is a significant reuse factor achieved in the application. You can reuse the data in the SRAM without the need to go to a DRAM or off-chip communication. And the order of, there will be an order of magnitude energy reduction, despite the fact that your tier-to-tier connection are not occurring at a lower capacitance compared to 2D. Because with 3D, you have both a high capacity and high bandwidth improvement that you see at the application. At the end, a significant energy gain is observed because of the cache capacity increase. So for these type of things, we have a lot of 3D solutions. So you are all familiar with this one. So I will briefly talk about it. So the fine pitch for the mobile, typically fan out package for imagers, there is no die size requirements. It's mostly wafer to wafer stacking. Heterogeneous integration is typically done in 2.5D form with interposer, or using, for instance, silicon bridge technology combined with omnidirectional interconnect proposed by Intel, which is delivering the power directly from the package to the dice without the need to go through the bridge. And there can be also coarse and fine-grained microbump connections to the dice. And then finally, again, a wafer-to-wafer stacking use case, which is the HBM. Today, we are in the HBM2E, HBM3 is on the way. So which is stacking today at 40 micron vertical pitch, vertical dimension of the tinning, and then 40 micron pitch, microbump pitch, connecting 12 DRAM stacks on top of each other. So, but which one is better? So there are a lot of pros and cons of what to select. It highly depends on the application. So here is quite a busy slide, but the essence of it is that there is one side, a maturity test, yield and performance side, and the second thing is the PP. So the second aspect is how to handle the overhead, like what type of infrastructure I need to have to be able to enable the full application. But in principle, these are the high-level observations. So hybrid bonding in PPA-wise is better than microbump, but there are significant test restrictions and more expensive than microbump. And also, in terms of the selection of whether we need to use face-to-face or back-to-face, thermal and also the complex integration scheme favors more face-to-face, but back-to-face for system scalability. And also test advantage is better in back-to-face. And then SRAM top and the bottom is mostly dictated by the power IR drop and the thermal requirement. And then one of the most important thing is the readiness level of 3D. For instance, if you put the SRAM to the top, then you need to wait in the logic technology, the enablement of the TSV technology. So there's a significant time to market penalty if the SRAM is adopted in the bottom. So here, this is just a high-level cartoon illustrating that. There is for last level cache application. If you choose the logic node and SRAM being the same node, then it's okay to stack them either back to face or face to face. But in this case, SRAM can be stacked below, and then SRAM can be implemented in the previous node generation. I'm sorry for my mistake here. So here, for instance, you have a 5 nanometer node or 3 nanometer node coming up. Immediately, you can focus on the logic node, release it right away, and you don't need to have any TSV technology adopted for the logic node. And the SRAM technology can be picked up from the previous node generation, like 5 nanometer nodes. And then this will allow basically to immediately release a product right away because of putting the SRAM to the below. But the biggest issue here is how to deliver the power to logic, non-good die logic test. And also there is a high cost associated if you implement through dielectric via or through mult via to deliver the PDN, for instance, from this region of where there is no any die. And then the other application is same node stacking. So you are here forced to use the same node. So then
10 minutes left. Okay.
Sure.
10 minutes.
I will.
Sorry.
5 minutes should be okay. And then we need to deliver basically logic node has to wait for the TSV process. But this process can allow multi-tier SRAM stacking. For instance, if it's a back-to-face implemented, there can be another SRAM put on top of this SRAM. And then also there is no need for the dielectric via because logic will anyhow get most of the power allocation from the interposer or package below. TESS is a big issue for non-good die test. For instance, when you get the wafers of the logic and the SRAM wafer, you can do a wafer toss sort test of the logic and the SRAM before. But if the SRAM wafer, let's say, in this case, SRAM and logic, let's say, because the surface of the SRAM has to be planarized and you need to use some sacrificial prop pads and then continue the hybrid bonding process. So this is not typically a product level test that is enabling this. You cannot apply a full product test at this level. So basically there is the complete assembly process and the SRAM yield has to be perfect to be able to do take cost advantage of the omitting the test of the pre-bond test for the SRAM. This is one of the challenge for the hybrid bonding test challenge. So the other things for sure related to the 3D process like thinning and then need for temp carrier. That's other risk factor we need to take. So compared to the 2D test flow, there's a significant difference and significant complexity required for the test. So I will skip this one. So another problem is the standardization. So there are a lot of standardization efforts ongoing. So one of the so HBM3 everyone knows. So the tendency is to we can go to 300 femtojoule, and the bandwidth is reasonably well. There is a interesting standard which is actually picked up by academy, introduced by Intel, and that's you see one example from the University of North Carolina. So implementing this AIB transceiver, and that's relatively going ahead for the interposer chip-to-chip communication. Interesting point about it, because you can connect the logic die next to another logic die, and it can be a good thinking for interface, standardized interface. So the cost reduction synergy is for 3D is pretty important, and that's one thing actually for the one of the cost reduction synergy is the number of metal layer reduction, because many of the dies do not require that many level of metals required for routing. And also the these parts, SRAM, for instance, is not scaling anymore. Likewise, the case on the IO analog and the other RF devices. So that's why there's a strong motivation to put the SRAM to disintegrate from the logic die. And also the selection of the VTs will be limited. So this will actually being a significant opportunity for the cost reduction. Another issue is the yield. So because of the die area increase, so because of the MPU function that I mentioned, significantly the mobile processor die areas are going about 100 millimeters square. At the same time, the amount of design rules, the basically associated with the process steps, the amount of process steps are increasing dramatically. So basically almost exponentially. And then therefore the yield is dropping, and also metrology to screen the particle to improve the D0 level in the fab is getting very, very difficult. So the one thing is actually putting a lot of things to the memory, exploiting redundancy and reducing the chip area by decoupling the memory is a strong motivation to improve the yield. So doing this, taking all these consideration, like process complexity, die cost, as well as the 3D integration costs. So the cost parity between the 2D and the 3D die is occurring around 150, 125 millimeter square area. So from that point on, any die size larger than that 3D is bringing a significant cost advantage. And also product bundling and also performance improvements that I mentioned. So that's why particularly being die sizes being larger for 3 nanometer node, it is economically more advantageous to move to 3D solution if it becomes a high volume solution. But how to use the 3D for a random logic routing probably is not a way to go. One of the problem is that if you do a complete place and route actually with a random logic die, you have more increase of the area because of the IP shadowing issue. And also the upper layers of the metals, they are not fine pitch. But these are very, very important layers for clock and power distribution and global routing. So you put a lot of blockages if you do tier-to-tier connection. Another problem is that the resistance increases dramatically. So the quadratic increase of the resistance here pushes a lot of routing to the upper layers mostly. Basically, upper layers are used more for utilization of the routing, and therefore there is no way to use the thing. The other problem is the pin density, because Moore's law is improving the pin density with DTCO. So this is not a true application for logic. But what we need to have some kind of a standardized, more vertical movement of the data with a buses and NOC, and particularly logic memory is a driving application at least for 5-6 years ahead. And then where do we heading? Because we cannot put the CPU below the memory that much effectively, but if we employ a parallel architecture, for instance, doing a controller below and then putting a non-volatile reconfigurable accelerator, it can be like a compute unit, like a Mac unit on top of the sequencer, and then several memory tiers where the data moves naturally vertical in this direction to create a multi-tier stacking system. This system also solves all the problems of the clocking and also dark silicon problem because of improved parallelism and the data movement enabling asynchronous communication interfaces. And this brings me to the takeaway. I conclude my presentation here. So mobile computing, cloud, edge, these are driving more scaling. Memory bandwidth and capacity extremely critical for enhanced PPA scaling, despite the fact that we don't have any much improvement in power and frequency, but at system level, we have significant improvements in performance and energy if we provide bandwidth, memory bandwidth, and capacity. Slowdown and pitch scaling, I've shown some examples of DTCO and STCO, lateral gate-all-around and fine pitch 3D VLSI as alternative. And the 3D stacking, so a lot of large silicon area trend is happening because of AI chips, and also especially memory bandwidth and capacity gain. While the cost gain in large chips, if we keep the application, target applications in this die area, then we have a cost advantage. Still, we need to solve problems of the non-good die test, EDA, and thermal PDN and I/O interfaces. But I think this is also seen a lot of examples that this is going in the right direction. Thank you so much. That's all from my side.
Thank you so much, Mustafa. This was really an excellent overview on the future developments. And for the more, let's say, really for the scaling of systems. Yeah, I think we are happy that the IDS predicts that 3D will play a key role there in the future, as we hoped decades before. No? Not only more than more. So the paper is open for questions. We have time for 2 or 3 questions. Paul, are there questions in the room? I don't know. Sorry for that. I don't know how to manage their questions in Rally, not online. Yeah, anyway, maybe I take the opportunity and have a small question. So if you see how the ITS roadmap worked before the IITS, they were introducing such red bricks where you really did not know when you do the, let's say, addition of the roadmap, the new version, how to solve this, maybe in 2 or 3 or 5 years. I don't see this in the IEEE roadmap, at least not in the more than more, but I think there will be some subjects that are not solved today. And I have a special question. So you mentioned the 2D materials, huh? Like molybdenum, disulfide, and so on. This is a new substrate, let's say. They are introduced as a substrate. It's not silicon technology anymore. So how to solve this in 3D? Is it, so you cannot speak of monolithic integration then. Is there any, yeah, this is my question.
It's a big challenge, and it's a 2D channel material growth is a big problem. In fact, any irregularity there immediately translates into performance, and also how to make a contact to 2D material is a challenge. So these are two challenges, like a substrate and the contact technology. But on the 2D side, this is probably the solution is really seen by 3D, like a layer transfer technology. So once that is coupled from the silicon technology, and then once a layer transfer technology taking a 2D material substrate and then transfer it to a carrier wafer or silicon wafer, I think this is the viable route to go. But probably from the 2D material, we don't see initially a solution directly replacing a silicon channel. It might be maybe as a complementary FET initially in the first generation. That's why that's a trial year. But afterwards, if it is becomes a 2D channel for gate-all-around device, then we need to think about there, because there the layer transfer technology will not work because it will become too expensive, because you need a lot of 2D channel material layers, or some kind of a spatial epi-like growth enablement necessary if you want to go for monolithic integration of 2D.
Yeah, thank you so much.